So the topic for today is analysis of pin-jointed frames, method of members. So previously, we discussed method of sections and method of joints. Now those are for what we call two-force members. Here in analysis of frames, we're going to talk about three-force members and then the actual method of members. Let's begin. So as I mentioned earlier, we have your three-force member. So what is that? So from the name itself, it is a member subjected to three or more forces applied at different positions. Now usually, or rather in our previous lectures, the forces were always at the joints, right? But now, for three-force members, the force can be applied along the length of your member. Okay? So that will cause bending action. Therefore, three-force members are also subjected to bending loads. And then, another characteristic of a three-force member is that it is a non-axial member that is not simply in tension or compression, unlike what we've been solving for earlier. So let me draw that. What is a three-force member? Let's take this beam, okay? And then let's have it simply supported. Remember, simply supported just means one end has a hinge, the other has a roller. Now, what if we remove that roller and we replace it with another hinge, okay? And then let's apply an external force here. So what will happen at the reactions? Well, for pin, same thing, you're going to have vertical and horizontal. So let's call this A, let's call this support B. So this is now AV. And then remember, for a pin, it has perpendicular and parallel reactions depending on the surface and the applied load. So a hinge can either have a vertical or horizontal reaction specifically for this type of system. And then we have another hinge there. So same thing, you're going to have vertical and horizontal reactions. Okay. Now, these two forces can actually be redrawn into a single force. It's resultant. Okay. So this is upwards to the left. So the resultant should also be upwards to the left. And this is your total reaction at A. And then it's going to be at a certain angle. Okay. So same thing here. Our drawing here is upwards to the right. So your resultant is upwards to the right. So that's your reaction, total reaction at B. And once again, it's at an angle. Okay. So in either cases, let's look how many unknowns we have. We have 1, 2, 3, 4 if we're going with the component method, meaning just getting the vertical and horizontal. Or we have 1, 2, 3, 4 if we're looking at the total reaction and their angles. So 4 unknowns, but the equations that we're working with are only 3, your 3 equilibrium equations, okay? So therefore, 4 unknowns, therefore, your 3 equilibrium equations are insufficient. Remember, sufficient. Remember, whenever you have, the number of unknowns that you have should equal the number of equations that you can make in order to solve for all of your unknowns. Okay, so 4 unknowns, 3 equilibrium equations, you can't solve for this type of problem yet. So what do? We're going to use your method of members. So let's talk about that. Now, moving forward, the type of structures that we'll be talking about are frames. So frames are pin-connected structures with some or all members in three force members, okay? So some of them can be actual members, again, similar to what we've solved for previously, or again, could be a three-force member, all or some. We'll have more examples of that later on so that you can see what that means. Now, to solve for these types of problems, you're going to use method of members. So it's a method where the free force member is disconnected from the structure and a free body diagram of the member is drawn. So method of members will be used whenever you have a free force member. Example here. Now, why can't we use method of sections or method of joints? Because method of joints, you're assuming that the force passes along your member, right? We have something like this. We're assuming the force are along the members themselves. Okay, but the trusses that we've solved for, all of them have been two force members. For all the members of the trusses that we've solved for so far are two force members. Now, for three force members, okay, if you isolate a support, okay, the force that will come out of here will not be the same direction as your member. So method of joints is not ideal. Same with method of sections. For method of sections, we use a cutting plane and pass through the actual members themselves. And we can't do that. For example, here, right, we pass a cutting plane, then you're going to find the forces. Now, for a three force member, can't do that because if you cut through a beam that is under bending load, it's going to have both the axial and a perpendicular reaction at where you slice it. So, for example, you have a beam, okay, cut out the cross section of that. There's going to be an axial force and a perpendicular reaction. So method of sections and method of joints aren't ideal for three force members. Okay? Now here are the principles of method of members. So when separating members for analysis, forces and their components exerted by the connecting pin must be consistently represented as acting opposite direction on the separate members. What does that mean? So for example, you have something that looks like this, okay? You have three members that are connected. So for method of members, what happens is you isolate the actual members themselves. Okay. Remember, for method of joints, you isolate the joint. For method of sections, you cut or use a cutting plane, then isolate either the left or right side of your structure. Method of members, you're isolating the members themselves. So let's say we isolate AB. So isolate that. You're going to draw a free body diagram of that. And then if these are hinges, remember hinges have horizontal and vertical reactions. So you have a hinge at A and at B. So for this part, you can either have an educated guess on what the directions of your forces are, okay? Or you can just guess entirely. That's fine. You're gonna get the correct magnitude of your answer, just incorrect sign, similar to, again, method of joints and method of sections. So we have this AV, AH, and this is BH, BV. Now that you've established this, okay, when you isolate BC, you're gonna use the opposite force that you established earlier. So that means, so this is B, this is C. BH is to the left for this member. So the connecting member should be to the right. So BH to the left, here it's supposed to be to the right. In the same way, this is upward, therefore this is downward. Okay? Yeah. So it's not about tension compression. It's not about towards the joint, away from the joint. No, it's about the actual direction, to the left, to the right, opposite on the other member, on the connecting member. Okay? So that is what that principle means. And then, if the direction assumed is incorrect, the solution will give its correct magnitude, but with a negative sign. It's the same process as your previous lectures. All right. So that's method of members. Let's have a few examples to better understand these concepts. So let's start with number one. Number one, the structure shown in the figure is pinned together at ABC and held in equilibrium by the cable CD. A load of 12,000 pounds is acting at the midpoint of member AB. and a load of 8,000 pounds is applied at point C. Determine the reaction at A, the internal force in member BC, and the tension on cable CD. So we're looking for three things. Reaction at A, internal force at BC, and then tension on this cable. Okay, let's solve. So let's analyze what's happening here. You have this structure being supported by your cable over here. Okay, and then what we're looking for is the actual value for tension in this cable, the force in member BC, this is your BC, right? And then reaction at A. So let's figure out what those are. Reaction at A, you have here a hinge. So once again, you can have horizontal and vertical reactions. So let's solve. Okay? So these are downward, so I'm going to assume reaction for A is upward. RA. Okay? And then, yeah, I'm just going to assume this is the direction for my RAH. This is RAV. Or you can write it this way, just AV and then just AH for horizontal and vertical reactions. Now, aside from that, you also have a support here, your hook supporting the cable. So what kind of reaction is there? So this is type of fixed support. So typically, it also has your vertical and horizontal reaction. But since this is just a cable, the reaction here is actually the same, or rather, it's the same direction as your cable. So it's this way, therefore it's also this way. Okay. And then same orientation. So what is the angle of this? This is 53, right? So that means, yeah, if I extend this, this is your 53. Opposite angles, this is also 53. So to get this, it's just 90 minus 53, which is 37. So 37 degrees for here. And this is your reaction. And this reaction is actually equal to the tension in your cable, since this is the only thing attached to this part. Okay, so this is your tension. Yeah. All right. So now let's solve for what's being asked. So we can start by order on which it was mentioned here. So let's try to solve reaction at A first. So reaction at A, even though this looks different, principle is still the same as your previous lecture. Usually when looking for reaction, we either start with moment or summation of forces X or Y. Now I want to get force at A. So you're going to get moment. I want reaction at A, so you're going to get moment on the other support, so at B. So let's take moment at B. Okay. AV is actually the same, or it's level with your reaction at B or support B. So therefore AV is ignored since it passes through your moment center. So we're left with AH. So AH rotated about B, that is counterclockwise. So negative AH. Now, next problem. What is the vertical distance? So you want to get this, okay? So let's try to solve for that first. I'm going to move this here. Yeah. All right, let's try figuring that out. Now look here, we have, if you've noticed, a couple of triangles. Okay. If I draw a line here, I can get this height by considering this is 30 degrees and then this is 16. So I have myself a right triangle, right? Same thing here. This is also a right triangle with angle 53. And then I just need to figure out what this length is. So let's give variables to that to easier find out or solve for those values. So let's call this X. I'm going to call this A. And then I'm going to call this B. Okay? So let's solve for each. So for A, that's easy enough, right? It's just this length right here. And once again, I'm given angle here, it's 30. Then I'm also given this length, which is 16. I'm given an angle and a hypotenuse. For this case, I'm looking for the adjacent length. So we're going to use cosine. So cosine 30 is equal to adjacent over hypotenuse. Adjacent is this, which is equal to x. And then your hypotenuse is 16. And then solving for x is just 16 cosine 30. And if you solve for that, you get 13.86. Now, preferably, you're going to store this in your calculator so that your final answers are more accurate. So now I have my x. Next, let's figure out the other values. Let's start here at A. So for A, since I already know this value, I'm given this angle, I'm going to use tangent, right? So tangent theta, which is 53, equals opposite, so that's x, over adjacent, which is your A. Okay? Again, considering x is 13.86, solving for A, we get 10.44. Once again, you're gonna, or it's preferable that you store this value. And then lastly, solving for B, again, considering this right triangle, I know this angle, right? Okay. This opposite side is actually also equal to B. So if I use sine equals opposite over hypotenuse, so I am able to solve for B. So sine 30 equals opposite. Again, it's this side, which is also equal to B. So that's B over hypotenuse. Hypotenuse is 16. So solving for B, it's 16 sine 30, which is equal to 8. So now you have your values. Okay. So therefore, you can continue solving here. Perpendicular distance of AH from support B, it's this total length, which is equal to A plus B. Yeah. So A plus B. Again, A is 10.44, B is 8. Next, we have 12,000 here, rotated about B. That's clockwise, therefore positive. Perpendicular distance, yeah. So extend its line of action. Perpendicular distance is this length, which is also equal to this. So that's 4. Next, we also have this 8,000, again rotated about B. Clockwise, therefore positive, 8,000. And then perpendicular distance. Okay, extending this line of action, perpendicular distance is this length, which is equal to x. So 8,000 times x. And I believe that's all the forces there, so equals 0. Okay, solving for AH, you should get 8,613.77. Unit pounds. My answer is positive, therefore correct assumption that AH is upward. Okay, so now I have AH. Next, I want to solve for AV. So how will I solve for AV? Now to get AV, okay, I have to figure out another force, which is tension. Okay. So the next step is to find out what's tension first. Okay. So let's solve. Because usually, if you remember, after solving for a moment, the next step is to solve for forces vertical or horizontal. If I take forces vertical and horizontal here, I'll have two unknowns for AV. Right? So let's do summation of forces horizontal first because I already know the horizontal reaction at A. Summation of forces horizontal equals 0. Let's do it here. Or I can move this here actually. Okay. So summation of forces horizontal equals 0. You have AH to the right, therefore positive. And then look for other horizontal forces. There's no horizontal external force. So therefore, we're left with this reaction for tension, which is to the left. So negative T, and then get the horizontal component, cosine 37 equals 0. And then from this, I can solve for T. So T is equal to 10,785.61. Okay. So now I have another force that is known. So now since I know T, I can go ahead and solve for summation of forces vertical to get AV. Okay. So AV is upward, therefore positive. What else? We have 12,000 here, downward, therefore negative. We have 8,000 here, so downward, again negative. And then we have this T, upward, therefore positive, and then get the vertical component, so that's sine 37. And then equate that to 0. Now this is why, again, we solve for T first, so that I can use this equation in solving for AV. Okay, so now that I know T, it's here, solve for AV. And again, you're going to want to store. Okay? So using the stored value, solving for AV, you're going to get 13,509.06 pounds. Okay. So now I have this. Let's look here. Okay. What we're looking for is reaction at A, not components of the reaction at A. So we need to get the resultant of AH and AB. So to get that, remember, to get the resultant, RA, it's just your AV squared plus AH squared. So square root of AV squared plus AH squared. So plug these values into your equation and solve for RA. You're gonna get 16,021.60 pounds. And then we're not done. After getting the resultant, you're gonna get the angle. So angle is just arctangent AV over AH. And then solving for that, you're gonna get 57.48. So 57.48 degrees. Okay, and then to get the direction, look at your values. AV is positive upward. AH is to the right. Okay. Again, positive answers, therefore correct assumption for reactions. So therefore, it's upwards to the right. So you can write out the whole word upwards to the right, or you can just denote it this way. Okay. So there. These are your first answers. And don't forget, this is also one thing we're looking for. Okay. Now next, we're looking for internal force in member BC. So we're looking for this. Okay. So this is C. This is your member BC. Now, some of you might be tempted. In order to solve for BC, you're going to solve for AC and AB first by method of joints or method of sections. And then you're going to move on to BC using joint B. Now that's incorrect. Why? Looking at member AB, it's subjected to a bending force, right? You're 12,000 pounds. Therefore, this is a 3-force member. And as I've said earlier, we can't use, or it's not advisable to use method of joints and method of members on 3-force members. So what are we gonna do? So you have two choices. You can still use method of joints and method of members. Just make sure you know where to use it. Okay? Let's look at joint C. Can I use it there? One force we have is tension. Okay? So that's obviously an actual force or an actual member because tension is just along your wire at all times. How about this? Member AC, there's no force acting on its length, right? Therefore, that's a two-force member. Same with BC, it's a two-force member. So I can apply method of joints at C. Okay? So you can try that. You can try solving for this using method of joints at C, or another method would be using method of sections. But we're gonna use this as your cutting plane. Okay? Right, so let's call this S for method of section. Okay? So at section SS. So remember what's method of sections? You're gonna pass through a cutting plane, then you're gonna isolate one of the sides. So you can isolate either this top side or this lower side. Now we can do either. I'm gonna choose the lower side. Okay, so just draw it the same way. So you have your hinge there. You have AB upwards. You have AH here, right? And then you have your member AB. So this is A, this is B. What else do we have? We have this, right? And this is your member AC. So that's your force AC. And then this is 30 degrees. What else do we have? We have this. Okay? And this is your force BC. Remember, for me, I just like to assume all of my forces are in tension for method of section. Okay, but again, you can use your educated guesses to figure out their actual direction. Okay, so our goal is to get FBC. Remember, for method of sections, the goal here is to figure out at what point do the other unknowns pass through. So that if I take a moment there, the only unknown now is what we're looking for. So looking at this drawing, I should take moment at A because FAC, AB, and AH passes through point A. So summation of moment at A equals 0. Okay. Oh, don't forget we have an external force here. So this is 12,000 pounds. And then this is 4. Okay. So all of these forces pass through A. So ignoring that, next we have 12,000. Rotate it about A, that's clockwise. So that's 12, 1, 2, 3. Perpendicular distance from point A, that's 4. Next, now what about this FBC? Okay, now remember, whenever we have a diagonal force, you have a choice to separate them into their components. So this is your vertical and horizontal component for force BC. Look at this horizontal component, it passes through A. So therefore, I can just ignore this. So now I'm left with the vertical component of FBC. Rotating it about A, that's counterclockwise, therefore negative. So you got negative vertical component of FBC. So how can I get that? Okay. So to get that, I need to know either its slope or its angle from the horizontal. Okay. So angle from the horizontal, it's this angle. Let's call that beta, since it's at point B. Okay. So BC is the same here. So this is your beta. Okay. Let's solve for beta. How do we get that? Again, you're gonna look at your triangles. So beta, what do we know? We know this is x. We know the value of that. And then this is 8. So to get, if I draw this line here and then this line, I get another right triangle. And then to get this adjacent side to your beta, it's just x minus 8, right? So I have an adjacent. Also, this opposite, this other leg is the same value as your b. So therefore, I can use your trigonometric function, specifically tangent, to solve for beta. Okay, let's do that. Let's do that here. Tangent beta equals opposite. So what's opposite to beta? Again, it's this. So that's b over adjacent. So what's adjacent? It's this length, which is again x minus 8, right? 4 plus 4, 8. So x minus 8. Beta, we already know to be 8. X is 13.86. Okay, so solving those values here, we can solve for beta, which is 53.79 degrees. Okay, so now we can get the vertical component of this. Again, we use the vertical component. So vertical, therefore, that's sine beta. So sine beta. Okay, and then perpendicular distance of the vertical component of FBC from A. So that's 4 plus 4. So times 8. There's no other force creating moment about A, so just equate that now to 0. Then from this equation, I can solve for FBC, which is 7,435.88 pounds. Positive, therefore correct assumption of direction. It's away from your member, therefore tension. So there. Those are your answers for number 1. Okay, we're done with number 1. Now let's continue on with number 2. But before that, the purpose of figuring out or solving number 1 is to show you the difference between 3 force members and then 2 force members, and to know if you're allowed or if it's advisable to use method of joints and sections if we're looking for forces in your member. Okay, so once again here, it's not advisable to use method of joints at point A, because again, one of those members is a 3 force member, and then your force here is not axial, meaning it's not along the direction of your member or not along the axis of your member. Okay, so that is just for teaching you the concept for method of members. Now let's move on to an example that's actually using method of members. Okay, so number 2. The frame shown in the figure is supported by a hinge at A and the roller at E. Compute the horizontal and vertical components of the hinge forces at B and C as they act upon member AC. So you have this figure. What are we looking for? Components of the hinge forces, B and C. So these are your hinges, B at C. Okay, and we're specifically looking for their forces upon member AC. So that means I'm gonna isolate AC, and the forces acting on that member is what we're looking for, specifically at hinge B and C. Okay, all right. So let's figure out how to solve for that. Okay, so remember, one of the things that we know is for sure I'm gonna have to isolate this, right? Now, if I isolate that, in order to analyze this member, I'm gonna have to figure out the reactions at this support because it's a part of that member. Okay, so that's the first step. Let's try to find out the reactions here. So once again, I'm gonna assume reaction at A, vertical reaction is upward, so this is your AV. And again, I'm gonna assume your AH. Okay? How do we get AV? You're gonna use your moment. I'm gonna take moment about the other support, so meaning at E. So summation of moment at E equals 0. Okay, so let's start. AH passes through E, therefore ignoring that. AV rotated about E, that's positive since clockwise. So AV, perpendicular distance, you can see here, that's 1, plus 3 plus 1, so that's 5. What else? We have this, 24 kilonewton, rotated about E, that is also clockwise, so positive. 24, perpendicular distance. The perpendicular distance is this length. And look here, this is 1.5, this is 1. So to get this, I'm just going to have to subtract 1.5 and 1. So that's 0.5. Okay, so solving for AD, we're going to get negative 2.4. So once again, whenever you get a negative answer, you have two choices. You're going to keep the negative and then keep the direction and make sure you're following this direction whenever you're solving. But you're going to use the negative sign when you're substituting the value. Or method 2, you're going to correct your mistake. So now we know this is 2.4 upward. Okay, so downward, right? Incorrect assumption, so this should be downward. So we can either correct that and then note, oh, this is downward. Okay? But for now, let's try keeping our mistake. Okay, so I'm not going to change that. Right. So now that I have that, what's the next step? So if I analyze ABC, this member, I'm going to have a lot of unknowns, right? So we have an unknown here and here. So that's 4 unknowns. So I'm going to have to figure out how to lessen one of those. So usually to do that, you're going to look at the other members connecting to those hinges. So you can either look here or look here. Now, if I look here, it's the same thing as the other side. I'm just going to take reactions here. Then once again, there's going to be unknowns. So most likely, this is what I'm going to isolate next. So let's try that. Isolate member AD. Okay. So this is your B. You have D here. And then we have an external force. Don't forget your external forces. 24 kilonewton. Okay, and then your distances. Okay, so from B to D, distance there is 3. So this is 3. And then from D to your external force, that's 1.5. Okay. So whenever you isolate a member, there's going to be horizontal and vertical reactions at each hinge. So we have a hinge at B. Once again, you're going to guess. Or you can get an educated guess on the reactions at B. Okay? So I'm going to guess it's upward. So this is your BV, and then I'm going to guess this is to the left. Okay, BH. Right? So remember, my goal is to get BHBV, CHCV, right? Components of the hinge force at B. So this is actually what I'm solving for as well. So I didn't have to isolate this to get BHBV. So now knowing that, okay, I want to know this. And to solve for this, you're going to use your 3 equilibrium equations. So if you've noticed, the steps are still similar to method of joints and method of sections, wherein you isolate and then use your equilibrium equation. So isolate, next equilibrium equation. So we have a choice between moment, forces vertical, and forces horizontal equals 0. Now, if I choose forces horizontal or vertical equals 0, okay, they're gonna have to take note that here at D, that's also a hinge. So therefore, that's also gonna have your vertical and horizontal reactions. So if you take forces vertical, you're gonna have 2 unknowns. Forces horizontal, you have again 2 unknowns. Okay, so instead, we're gonna do moment at D. Okay, actually, let me just include these as well. Okay, I'm just gonna guess that. Just so you know that there's gonna be reactions at this hinge. Okay. So once again, so that I don't have to deal with that, I'm going to use moment at B equals 0. You will remember whenever we have an unknown that you don't want to deal with, you're going to take moment at that point. All right. So take a look at BH. It passes through D. So ignoring that. Next, BV rotated about D. That's clockwise. Therefore, positive. BB. Perpendicular distance of BV to D is 3. DH and DV passes through D. So ignoring that. And then now you have your 24 kilonewton rotated about D. That's also clockwise. Therefore, positive 24. Perpendicular distance 1.5. Okay, solving for BV, you're gonna get negative 12. Okay, so therefore my assumption is incorrect. It's supposed to be 12 kilonewton downward. Okay, and that's actually one of the things I need to solve for. Again, components of forces at B and C. This is one of those components, your BD. Right, so I already know one thing. Next, how can I solve for BH? Okay, so looking here, the only way to solve for BH is if I know BH. Okay, for forces horizontal equals 0. But I don't. So I'm going to leave this and then I'm going to move on to the next member since I can't solve for what I need anymore. Okay, so now let's try isolating A, B, and C. Okay, so you have your AV and AH. So for reactions, you don't have to worry. You're just always copying what you drew on your diagram. So AVAH upward to the left, but take note again, that's negative, okay? So AVAH. By the way, what's AH? Well, we have a roller here, right? Meaning there's no horizontal reaction at a roller, right? There's no parallel reaction. There's no parallel reaction. There's no horizontal reaction at your support here. There's no horizontal external force. Therefore, AH is 0. Okay, now it's a different story if this is also a hinge. Okay, so that means there's gonna be a value for AH. But since this is a roller, there's no horizontal reaction here. AH is 0. Okay, so you can draw that or you can ignore that since there's no value. Okay, so now you just have AB. Next, you have your B here. Now remember what's said earlier. For hinges, for method of members, forces are opposite of what you originally assumed. Okay, so meaning I assumed BH is to the left on this member. Therefore, here I should write the opposite, so to the right. Okay, same thing here. Now, for this case, okay, this is incorrect assumption. I know this is downward. So you're not going to repeat the same mistakes anymore for method of members, okay? It's better to correct it so that you won't get confused. So this is downward. I already know downward. Therefore, this should be upward. Okay? So for method of members, if you know already what the actual direction is, you should apply that. So I know this is downward. The opposite of that is upward. Okay? So this is your BV. Next, CH and CV. So since I have no prior assumptions for that, I can just guess here, or again, you can create your educated guesses. So this is your CH, this is your CV. Okay. So I have BV, right? If I want to go for BH, okay, we're going to analyze this member. So my unknowns are CH and CV, and then BH. So remember, whenever we have unknowns, one way to get rid of that is to take moment on that point. So that means I'm going to take moment at C. So summation of moment at C equals 0. From that, I am able to solve for BH. So let's solve. Starting with AB, rotate that about C, that's clockwise, therefore positive, AB. Next, get the perpendicular distance. To get the perpendicular distance, look at your original drawing. Extend your line of action for AB, and then this is the perpendicular distance from C. And what is that? It's this line. So this is 1. Since this is symmetrical, therefore this line divides the entire structure into 2 equal parts. So therefore, if this is 3, this is 1.5. All right? So 1.5 plus 1, that's 2.5. So that's the perpendicular distance. So AB times 2.5. Next, BV. Rotate it about C. Once again, that's clockwise, therefore positive. BV, perpendicular distance. Look here again. This is your B. This is your BV. This is the perpendicular distance. And what is that? It's half of 3. So that's 1.5. Next, BH. Rotate BH about C. That's counterclockwise. So negative BH. Perpendicular distance. This is your BH. This is the perpendicular distance, which is equal to this. So that's 3. Okay, there's no other force, right? For this member. So equate that to 0. CH and CV passes through C. So again, ignore that. Okay, AV is negative 2.4. So negative 2.4. Since again, I didn't correct my direction here, I'm still using upward. So you have to include the negative. So negative 2.4 times 2.5. BV, I corrected it already. So we're going to use the positive value. So 12 times 1.5 minus BH times 3 equals 0. So if you solve for this, you're going to get BH equals 4. Positive, therefore correct assumption, it's to the right. Okay, so you have one more down. Okay, now how about the others? Remember, after moment, you have force X and force Y equals 0, or horizontal, vertical equals 0, so you can go with that. So we can start with either. My preference is just vertical, so equals 0. AV is upward, therefore positive. BV upward, positive. CV downward, equals 0. Sub in your values, again, AV is negative 2.4. BV is positive 12 since I corrected it already. Minus CV equals 0. Solving for that, you get CV equals 9.6. Positive, therefore correct assumption downward. So this is what I mean by, for me, it's easier to correct these types of forces on the next member. Okay, because as you can see, if I didn't, then this would have been downward, and then I'm gonna have to remember, oh, this is negative, so this should be negative. Okay, so you can do that. You can still keep your original assumption. Just don't forget it's incorrect, so it should be negative. Okay, so you should practice what you're used to, so that you don't have to think about this too much anymore. Okay, so now I have CV. And then naturally, the next is summation of forces horizontal. So you have BH to the right, so positive BH. CH to the left, so minus CH equals 0. Therefore, CH is just 4 kilonewton. And then positive, therefore correct assumption to the left. Okay. And that's all we're looking for. So that's number 2. We're done with that. Next, let's move on to number 3. Number 3 is a bit similar to number 2. It's just still a frame and looking for our reactions. So number 3, the frame shown in the figure is hinged. two rigid supports at A and E. Find the components of the hinge forces A and E and the forces in members BC and BD. So we're looking for four things here. First, reactions at A and E. Okay. Components. So that means that's AVAH, EV, and EH. Right? Components. And then force in BC and BD. Okay, so let's solve. So let's mark what we want. We want to know force here and force here. Okay, and then the reactions here. All right. So once again, you're gonna guess the direction, or intelligent guess, or educated guess. To do that, just look here. I have an external force downward, therefore probably this is upward for here. That's your AB. And how about AH? So with this entire thing, due to this force, is gonna sway this way, right? Okay, so therefore there's gonna be a force here, rather at this joint, it's gonna be pulled away, right? Because of this. So to counter that, the reaction here is to the left. Okay, so that's your educated guess. Or again, if you want, you can just randomly figure out or guess what the directions are. Up to you. And then here, again, because of the external force, I'm gonna guess this is upward to counter that. Since again, all of this should be in equilibrium. So this is your EV. And then we have a horizontal force to the left here to keep everything in equilibrium. To counter that, your force here should be to the right, since there's no other horizontal force. Okay? So this is your EH. Yeah. Well, now let's start solving. So remember, or recall, whenever we want to look for reactions, we usually take moment about the other support. So if I want to start at A, let's take moment at E. Okay. So summation of moment at E equals 0. So AV passes through EV, so ignoring that. EH rotated about E, that's counterclockwise, therefore negative AH. Perpendicular distance is this length, which is equal to 2. So AH times 2. Next, we have 12 rotated about E, that is clockwise, therefore positive 12. Perpendicular distance, it's this length, which is equal to 2. Okay? There's no other external force, therefore solving for AH, that is 12 kilonewtons. And then positive, therefore correct assumption, it's to the left. Okay, so that's one down. Next. Since now I know AH, if I use summation of forces horizontal equals 0, okay? AH to the left, therefore negative AH. EH to the right, therefore positive EH. There's no other horizontal force, so equals 0, therefore EH equals 12. Positive, therefore correct assumption, it's to the right. Okay. Now what? Okay. Now let's try, what if I use summation of forces vertical? Okay. So if I use summation of forces vertical, I'm gonna have two unknowns. Okay, so you won't be able to solve for anything yet. So now that means I've exhausted all of my equilibrium equations. You're either gonna use method of sections, joints, or members. All right. So since I want to know AV or EV, I can either isolate this or this to get one of those. If I isolate this, I'm gonna have to know reactions here. So that's more work. So instead, I'm gonna isolate this instead. Okay, so isolating AB. So writing your forces, you have your AV. Again, for supports, you copy the direction. Okay. So this is AH. Next, there's an external force here. So don't forget that. 12 kilonewton. And then there's gonna be reactions at this side as well. Okay. So again, you can just guess. So this is your B, H, BB, right? And then we have 2, 2. So once again, the goal is to get AV, right? I already know AH. So to get AV, I'm going to take moment at this point. So this is point A, this is point B, right? So that I can cancel out these unknowns. So summation of moment at B equals 0. AH passes through B, so ignoring that. Next, AV, rotate it about B, that's clockwise, therefore positive AV. Perpendicular distance, 2 plus 2, 4. Next, 12, rotate it about B, that's counterclockwise, therefore negative 12. Perpendicular distance 2. BHBV passes through V, so ignoring that, passes through B, so ignoring that. There's no other force, so equals 0. Then from this, I can solve for AV, which is 6 kilonewtons. And then positive, therefore correct assumption for AV, it's upward. All right. Now, how do I get EV? To get EV, you can go back here, okay, and take your summation of forces vertical. So from original figure, okay, summation of forces vertical equals 0. AV upward, EV upward, so positive. And then we have an external force downward, so minus 12 equals 0. Knowing that AV is 6, you can solve for EV. And then EV is 6 kilonewtons. Positive, therefore correct assumption, it's upward. Okay. So now I've solved for all of the components of our force. Next up, I need to know these, okay? So once again, you might be tempted to use some method of joints here and then method of joints here, right? No, incorrect. Why? Member AB is a 3-force member because it experiences a bending force. Okay? So you can't use method of joints here. What else? Well, what about here? Can I use method of joints? No, because we have an internal hinge here. Okay? So we can't do that. So you can use method of joints. How about method of sections? Well, the only rule for method of sections is that it should only have or passes through 3 members. Also, make sure all of your members are 2-force members. So let's check here. Let's say I want to pass my plane here, right? Because this is what I want to look for, and usually we're passing our plane through members where the forces we're looking for. Okay. So let's check. That's only 2. So first criteria passed. Next, is BD a 2-force member? Yes, because there's no force along its length. There's no bending force present. How about BC? Is there a bending force present? No. Therefore, that's also a 2-force member. So I can use method of sections. Okay. So by method of section, okay, you're gonna isolate. So you can either isolate the top or bottom. Okay, for me, I'm gonna isolate the bottom so that I don't have to include this external force. So isolating the bottom, you have your point E here. This is EV. This is EH. Again, for supports, you're just copying the actual direction. And now, okay, draw this. Once again, for me, I just like all of my forces for method of section to be in tension. So I'm going to assume in tension, and then this is F, BD, and then this is BC. So FBD, and then this is FBC. We're looking for both. So what we can do here is we're going to take moment about one of your points, okay? I'm going to take moment about this point at D. This is D. Why? Because if I take moment at C, I'm going to have to solve for the components of this, right? Since it's diagonal. So just to avoid that, I'm going to use moment at D. Okay? Great, let's start. EH passes through D, so ignoring that. EV rotated about D, that's clockwise, therefore positive. Perpendicular distance, that is 2.5, and then this is 1.5. So that's 2.5. Okay, FBD passes through D, so ignoring that. FBC rotated about D, that's counterclockwise, so negative. FBC, perpendicular distance, 1.5. And then there's no other force, so equate that to 0. So using this, you can solve for FBC. Knowing that EV is 6, FBC is 10 kilonewton. Positive, therefore correct assumption, it's tension since away from your member. Okay, now how do I solve for FBD? So you can either use forces vertical or horizontal. Okay, so up to you. Let's try using summation of forces vertical. Okay, I'll move this here. Just so I have more space. And okay. Summation of forces, again, your choice, vertical or horizontal, you're gonna get the same answer. Let's try horizontal. Well, 0. Okay. I chose horizontal just so there's less forces since I'm not gonna include FBC anymore since it's vertical. Okay. So horizontal, EH to the right, therefore positive. What else? Here. FBD, it's to the right, therefore positive, and now I have to get the horizontal component of that. So how? So let's look here. This is your BD. I'm given dimensions, so I need to figure out its slope. Okay. So if you look here, this forms a right triangle, right, with base 1.5 and then height 2. So you can solve it this way. Square root of 1.5 times 1.5 squared plus 2 squared. We're going to get 5 over 2. Or if you've noticed, if I multiply both of these by 2, 2 times 2, that's 4. 1.5 times 2, that's 3. Get another 3, 4, 5 right triangle. Okay. Again, you can just use 1.5 and 2. That's fine. Okay, or you can use the 3, 4, 5 considering it's the same slope. Okay, so I'm gonna use that, the 3, 4, 5. We're using forces horizontal. So horizontal is 3 over hypotenuse 5. So plus FBD. Again, horizontal component was 3, hypotenuse 5. Okay, there's no other horizontal force. So equate that to 0. Solving for FBD, you get negative 20. Therefore, it should be 20 kilonewton. Incorrect assumption, tension, it should be compression. And that is your final answer. All right. So now we're done with number 3. Okay. So now since we're done, let's move on to number 4. So you have something that looks like a truss. So it's a bit similar to your method of joints and sections. So let's see. A three-hinged arc is composed of two trusses hinged together at B in the figure. Compute the components of the reaction at A and find the forces acting in bars A, B, and AC. So we're looking for reaction at A, and then bar components of reaction at A, and then force in A, B, and AC. Okay, so let's analyze. So this is what we're looking for, reaction at A. Okay, once again, I'm gonna guess vertical component of the reaction is upward, so AB, and then I'm gonna guess this is your AH. Okay, so one of the advantages of making an educated guess, if you look at number 3, all of our answers are positive. So you don't have to deal with thinking if I'm gonna correct the negative or if I'm gonna continue with the sign or continue with the direction. Just know that it's a negative sign. So this is an advantage of making an educated guess. Right. Once again, the goal, get these two and then find out force in AB and AC. This is AB, force AC here. Okay, let's try. So as usual, we're looking for a reaction. So I'm going to take moment about the other support, which is G. Summation of moment at G equals 0. AH passes through G, so ignoring that. AV rotated about G clockwise, therefore positive. Perpendicular distance at 6, 12, 18, 24 times 24. What else? You got your 36. Rotated about G, that's counterclockwise, so negative 36. Perpendicular distance is 6, 12, 18. And then you have your 60 rotated about G, again counterclockwise. So negative 60, perpendicular distance is 6, equals 0. Solving for that, we get AV is equal to 42 kilonewtons. Okay. 42, positive, therefore correct assumption, it's upward. Now what about AH? The other support is another hinge. So therefore AH is not 0. Okay? Because there's going to be a horizontal reaction here as well. GH. Right? So no, AH is not 0. So what now? So remember, when you're done with your equilibrium equations, you're going to either do your method of sections, joints, or members, whichever is more ideal or suitable to what's being asked. I want to get AH. If I use method of joints here, I'm going to have 3 unknowns, right? AH, force here, and force here. So cannot solve. If I use method of sections here, once again, I have 3 unknowns. So no. So we're left with method of members. So how will that work? Okay. Am I gonna isolate AB? Right? So I'm still gonna have 4 unknowns, right? Same with AC, that's also 4 unknowns. Now, for method of members, you're not just constrained to actual members themselves. Okay. You can isolate entire parts or structures as long as they're just hinged. So for example here, this is a hinge, so I can isolate that. Okay. So you can isolate any structure that is connected by hinges. So once again, I'm going to isolate this whole thing. Let's do that. Let's start here at A. This is AV. This is AH. And then draw Okay, this is C. Yeah. Okay, this is D. And then, okay, let's fix our drawing. Okay, that's better. This is C. This is B. There's an external force here. 36 kilonewton. And then dimensions, this is 6. And then this is also 6. Okay. Okay. So I've successfully isolated that. Again, this is A, B, C, D. Right. What's the goal again? Getting AH. Now I can get that by using this free body diagram. Remember, you can take moment about any support, any hinge, any connection. I have a hinge at D, so therefore I can take moment at D. So it's similar to what we did earlier. We're taking moment about the hinges. So this is also a hinge. Alright, let's start. AH, rotate that about D. That's counterclockwise, so negative AH. Perpendicular distance is this height. Is it given? Yes, it's 9. So this is 9. So negative AH times 9. Next, AV, rotate that about D. That's clockwise, therefore positive AV. Perpendicular distance, okay? Extend line of action, it's this, which is also equal to this, so that's 12. What else? 36. Rotate that about D, that is counterclockwise, so negative 36. Perpendicular distance is this length, which is again equal to 6. Okay, check if there's any other forces. No more. So equate to 0. Knowing that AV is 42, okay, you can solve for AH. So AH is equal to knowing that AV is 42, yeah. Solving for AH, you're gonna get 32. Positive, therefore correct assumption to the right. Okay. Now I have AH. The next goal is to get forces here. So once again, you're gonna check, can you do method of joints or section? Can I do method of joint? Okay, now I know this. Is this a two-force member? Yes, there's no bending forces acting on it. Same thing with AC, there's no bending forces acting on it. So I can use method of joints. In the same way, you can also use method of sections. Okay. But it's better to use method of joints. Okay, so at A, okay, oh, wala na akong space. All right, let's move this. Yan. Yan. Okay, better. Okay, so joint A, we have again AV, AH, then the members of your truss. So intelligent guess or educated guess. This is upward, therefore I need a downward force to put this into equilibrium. There, and then I already have a force to the left and right. So I'm just gonna guess this is to the right. So this is your FAB. This is your FAC. Okay. So method of joins, you already know how to solve for this, right? So let's go through the steps. So let's start with summation of forces. Vertical, so that the only unknown is FAB, since this doesn't have a vertical component. Right, so AV is upward, so positive. FAB is downward, therefore negative. FAB. So now I need to get the vertical component. How? So we're gonna check this, the slope. Okay, to get the slope, look here, this total height is 9. So if I draw this, I can consider this my right triangle, and this is the same slope. Height 9, so this is 9. And then total base is 6 plus 6, 12. Now, once again, look here. What if I divide all of those by 3? Okay, 9 divided by 3, that's 3. 12 divided by 3, that's 4. Once again, I have another 3, 4, 5 slope. Or again, you can just solve square root of 9 squared plus 12 squared. You're going to get the same thing. Now, I do this just so I don't have to solve, okay? I'm happy whenever I get a 3, 4, 5 triangle. Because you already know hypotenuse is 5. Great. So once again, we're solving vertical. So vertical is 3 over hypotenuse 5. So 3 over 5. There's no other vertical force, so equate that to 0. Knowing that AV is 42, you can solve for FAB, and then you should get 70. Positive, therefore correct assumption. AB towards the point, therefore that's compression. And then now we can solve summation of forces horizontal equals 0. Okay, AH to the right, therefore positive. FAB to the left, therefore negative. FAB, get the horizontal component. Horizontal is 4 over hypotenuse 5. And then FAC to the right, so positive FAC. There's no other force, so equate that to 0. Knowing that AH is 32, FAB 70, you can solve for FAC. Okay, solving for FAC, you should get 24 kilonewton. Positive, therefore correct assumption, away from the point, tension. And that is number 4. Okay? So once again, you're not constrained to just isolating one member at a time. You can isolate an entire structure, like what we did here. Oops. Yeah. All right. And then let's move on to our last example, number 5. Okay, it looks a bit different. Okay. Let's read. A beam carrying the load shown in the figure is composed of 3 segments. It is supported by 4 vertical reactions and joined by 2 frictionless hinges. Determine the values of the reactions. So pretty straightforward, we're just looking for reactions. And lucky for us, the reactions are already given. So these are what we're looking for. And then we have what we call your internal hinges. So what are those? So just think of it as the same as these things. Okay? So that means you can isolate the member between those hinges. Right, so let's start. So look here. Okay? Again, I have a hinge there. And then this is just free hanging, meaning I can isolate that. Okay? Again, whenever you have a hinge, you can isolate between those. So this is my hinge. Let's call that A and B, just so I have a name for it. A, B. Okay. This is what we're looking for, R1. This is a hinge. Therefore, there's also internal reactions. The same way, Okay, we have an external force 40 here. Now, if you've noticed, 3 meters to the left, 3 meters to the right. Okay, and then I have a hinge there, which could have a horizontal or vertical reaction. Now, if I draw this, since I call this A, I'll call this RA. And then there's no horizontal force, so there's no horizontal reaction. And we can say this is symmetrical, right? Along the vertical axis. Left side looks like the right side. So it's easy to solve for R1. So by symmetry, okay, R1, okay, left equals right. So R1 equals RA. And these two reactions will just share the load, okay, meaning total load divided by 2. So that's just, the total load is 40, so 40 over 2. All right? Now take note, if there's another external force here, then that's not symmetrical anymore. You're going to have to go through moment, force, vertical, horizontal, okay? But since this is right at the middle, 3, 3, right? It's symmetrical. Right, next. I have solved for, R1, 40 over 2, that's just 20 kilonewton. All the directions are already given, so you don't have to think about that. Okay. Next, let's find another thing that's symmetrical. If you observe, if I isolate this, again, I have another hinge there, so I can isolate. Isolating that, let's draw. Okay, we have B here. So there's gonna be a vertical reaction there. And then this is R4. Okay. This is 6. And then we have an external force. A uniformly distributed load. Which is 10 kilonewtons per meter. Now what about this? Is this symmetrical? Yes. You have an external load being shared by these two members because left side equals right side. Once again, if there's a force here, that's not symmetrical anymore. If this is triangular, that's not symmetrical anymore. Okay? Symmetrical, uniformly distributed, or force is exactly at the middle. Okay, so once again, I can solve this by symmetry. Okay, R4 equals RB, which is equal to, again, total force divided by 2. This is a uniformly distributed load. Remember, to get the equivalent force of that, just take the area. So area is 10 times base, which is 6. Then divide that by 2. You're going to get 30 kilonewton. Okay. Now, you're wondering why am I sure these are upward? Because these are reactions. And all my forces are just, external forces are just downward. Okay. Now I'm done. R1 and R4. Now I'm left with R2 and R3, and the final segment would be this. So isolate that as well. Remember, you can isolate segments that are between hinges. Okay, so this is between A and B. So draw. So remember, when you have assumed direction previously already in other members, remember, if you have a connecting member, it's the opposite direction. So here, RA, this is upward, therefore on the connecting member for this segment, this should be downward. Okay, so this is now RA. Reactions are the same. This is R2. This is R3. And once again, you have a reaction here, B. I assume B is upward here. So now do the opposite for that, downward. Okay, RB. And then we have an external load from A to R3. And that is equal to 20 kilonewton per meter. And then distances, this is 4, this is 10, this is also 4. Okay. So now the goal is to get R2 or R3. So recall, whenever we have two unknowns, you're just going to get the moment about the other unknown. So let's take moment about R3. So let's do that here. Summation of moment at 3 equals 0. Let's start with RA. Rotate RA about 3, that's counterclockwise, so negative RA. Perpendicular distance 4 plus 10, that's 14. Next, R2, rotate it about R3, that's clockwise, therefore positive R2, perpendicular distance 10. What else? R3 passes through 3, passes through the point, so ignoring that, so we're left with RB. Rotate that about 3, clockwise, therefore positive, perpendicular distance 4. Now we're not done. Remember, we have this external load. And that external load has an equivalent force at the center of that shape, right? Which means this is where that force will be. This is just a rectangle, so that's just between or at the center. So this is 14, so it's at 7. So this distance is 7. This also 7. All right? Okay. Okay. So actually, let me draw that properly. Yeah. Okay. So this is your force, equivalent force. The center of your drawing is the center for rectangle, so that's just 7 and 7. All right. So rotate that about 3, that's counterclockwise. So negative. Get the equivalent force, which is just the area. So that's just 20. Multiplied by base, 4 plus 10, so that's 14. Multiplied by distance. This is your equivalent load. Distance from R3 is this, which is again 7. There's no other force, so equate that to 0. Let's double check if it did the same, if it did correctly. Okay. 14 and 4. Correct. Okay, and then now we can solve for R2. Because RA, we know that to be 20, R2, 30, RB, also 30. So we can solve for R2. Sorry, RB is 30. We can solve for R2, which is 212 kilonewton. And now that we know R2, we can use summation of forces vertical equals 0. RA downward, so negative RA, positive R2, positive R2. We have downward force, like downward distributed force, so negative, and then equivalent force again is just the area, so 20 times base is 14 plus R3 since upward, and then minus RB. Equate all of that to 0. Again, RA is 20, R2 is 212, RB is 30. I can solve for R3. Again, let's double check if we wrote that correctly. RB plus R2 plus R3 minus RC minus RB 2014. All right, correct. Solving for R3, we get 118 kilonewtons. Okay. And that ends number 5. Okay. So for reactions, there are 4 answers. So that ends the topic for method of frames. Next meeting is friction in your structure.